today. But your pre-lab, because it's a multi-week experiment, you need the entire pre-lab completed before you come to lab this week. So you need the pre-lab for experiments 1, 2, 3, and 4 of parts of experiment 7. So all 3 parts of experiment 7. We'll have a quiz this week as usual. Make sure bring calculators, so forth for your quiz. On Friday, we have a division seminar at 3 o'clock. So the open lab is going to close at 2:30 on Friday. We also have a chemistry seminar at 4 o'clock. So make sure you attend that at 4 o'clock in 1000. And the division seminar is in Graves at 3 o'clock. Next week, we'll finish experiment 7. We'll do parts 2 and 3. Also, your rewrite for experiment 3's conclusion is due. 2 pieces here. So we'll talk about these in lab this week, and so know that next week you want to make sure for next week you understand all the corrections in your experiment 3 report because you're rewriting that conclusion for a separate grade. Okay. In 2 weeks, we're going to do experiment 8. Next week, I'm going to talk a little bit about things you need to prepare for that next week. And then this is one you want to make sure you should read all the experiments very carefully. Experiment 8, read like super carefully so that you've got all the pieces you need for that. So we'll talk more about that next week. And then your experiment 6 report is due in 2 weeks. Then if you're attending the Medical Missions Conference and you're in a Thursday lab, see me after lab lecture today because I need to start working with people who are in Thursday labs because we'll have to get you into a Tuesday lab that week to make up the lab. The lab we do that week is not one you can make up in open lab. Okay? All right, so let's start with experiment 7. Let me give you a little overview of what we're going to look at with experiment 7, and then we're going to talk about polymers in general before we get to the specifics for this week. So this week we're going to be starting with ethylbenzene, and we are just going to be doing this first reaction. So we're going to use NBS and benzoyl peroxide and hexane. And we're going to do this reaction at reflux, so there'll be heat. This reaction is a free radical benzylic. We'll talk about why that's important here in a little bit. Bromination, radical bromination. Forget that part. And so here is what we're going to get this week from step 1. We are going to brominate our ethylbenzene, and this is the product you are going to get for this week, okay? Then next week, we're going to take that product and we're going to use the base quinoline, and we'll talk about why that's important next week. And you're going to do the second step, which is dehydrohalogenation. So it's kind of like what it sounds like. We're going to take a hydrogen and a halogen off. And we'll get from that our styrene. Then the last step, we're going to use what's called AIBN. I'll show you what that is here in a second. In toluene. And heating that up, we've got our step 3, which is a radical polymerization. And so what you will be getting out of this then is we'll be making polystyrene. So here's the general structure for our polystyrene. This part off the end here is coming from the AIBN, so we'll talk about where this comes from next week. but this will be your final product from the 2 weeks of experiment. So a couple things here. First of all, NBS is N-bromosuccinimide. And so this is what the NBS looks like. Our benzoyl peroxide. There's benzoyl peroxide. And then our AIBN, which is otherwise known as 2'-azobis. There's our two pieces here, or first piece, sorry, azobis, isobutene nitrile, butene, sorry, got part of butene nitrile. So A, I, B, and then our N is this guy. So as we discuss these reactions, we'll talk about what each of these pieces, why they are important, okay? So since our eventual end with experiment 7 is we're getting to making a polymer at the end of experiment 7, we're going to talk a little bit about the chemical history and what's involved with polymers and what point we've gotten to as far as today. So a little bit of nomenclature with polymers. First of all, polymers are really large molecules that are put together with covalent bonds, so like molecular weights of thousands, 10,000s, 100,000s. And they're put together with smaller molecules, okay? So they start as monomers, and then if you put 2 of your monomers together, you get a dimer, then a trimer, and then finally, eventually, when you put a bunch of them together, you get what is called the polymer, okay? And so when we're talking about our polystyrene is going to have molecular weights in the thousands to 10,000s or so. So polymers, first of all, we didn't always use synthetic polymers. We first started using naturally occurring polymers, and one of the biggest ones was the rubber from the rubber tree. That's initially where rubber came from for tires and so forth. But then people started working with the rubber and decided, well, it needs a little bit of a modification to make it a little bit better. So people started working on just modifying naturally occurring polymers. And then they decided, well, we can make better things. So they started synthesizing polymers that had new properties that polymers had never had before. And so this is kind of going on a small scale, but then we had December 7th, 1941, that really changed how the history of polymers was going to play out. So what was that date? December 7th, 1941. Pearl Harbor. So the U.S. entrance into World War II is what made a huge, huge difference in the history of polymers. So what happened is at that time, President Roosevelt determined that one of the biggest things that was going to either make or break the U.S. Forces, whether they would win or lose in the war, was whether they had enough rubber for the effort. And so immediately, things kind of ramped up because they needed to find other sources of rubber to be able to supply what they needed for supplies to fight the war. And so look at here like a difference between natural rubber versus, I'll show you here in a minute, vulcanized rubber, or rubber with some synthetic adjustments. So with natural rubber, before you stretched it, it would just kind of fit into its space, and then you could stretch it out, but when you would have the rubber come back together again, when it's natural rubber, it never is quite exactly the same, it's never quite exactly the same shape and size as before it was stretched. And so vulcanized rubber, when we started amending what original rubber was like, we started putting cross-links in between the strands of the rubber, and so it was chemically enhanced. And what that did is then when it was stretched and it came back together again, it would come back to its original shape and size. So that really helped as far as this problem, okay? But then it started the process of what else can happen and what else can be modified. So some of the like macromolecular architectures that these different polymers can take on, both synthetic and naturally occurring, are you could have just a polymer that's just a linear polymer. You could have a polymer that's linear with branches on it, so that'd be a branch polymer. You could have a polymer that all starts from the same central core and then radiates out. So that's a star polymer, kind of like lipids. You can have a cross-linked network, which is like what ended up happening with vulcanized rubber. Or you can have this dendritic shaped macromolecular structure where you have this core, but different than the star, you have the core and it branches, and then off those branches, there's more branches and more branches off of that. So those are just some of the different big picture structures that polymers can take on. And so looking again at just how the individual molecules are put together, they can be randomly put together if you have more than one. So if you have things that are more than one monomer, so in our case, all our monomers are going to be styrene, so this wouldn't apply to what we're eventually going to do. But what you can do is you can put multiple things together as far as copolymers, and they can end up bonding to each monomer randomly. You can have it set up in the synthesis that you put together one block of the copolymer and then put together another block. So I'll show you an example of this here in a second. Or you can have where you alternate synthetically the different monomers that are present back and forth throughout. And so I'll show you an example of that. So an example of a block copolymer is saran wrap or plastic wrap. It is made up of ethylene and acrylic acid, and so there's blocks of ethylene that add to the strength of the polymer, and then there's the acrylic acid that's put together, and this is the part that's the sticky part that actually sticks to the glass and makes in hydrogen bonds with the glass to make it stick, okay? So this is why plastic wrap works for glass but doesn't really work for plastic, because plastic doesn't have its things for it to hydrogen bond with. So when making food wrapping, they make blocks of ethylene polymer and then blocks of acrylic polymer and put acrylic acid and put the two of them together, okay? This is an example of something that's even like a common demo in general chemistry is making nylon. This is an example of an alternating polymer. So you take a dipolyl chloride and you take 1,6-hexane-diamine, and at the interface of the two liquids, you get the nylon to form at that interface. And the nylon is a piece of a dipolyl chloride and a piece of 1,6-hexane-diamine alternating together, okay? And so this is that demo, if you've ever seen it, where they start pulling with like wire and start pulling up the nylon that forms at that at that interface. And so, just like rubber was really important, actually figuring out how to synthesize nylon was really important to the polymer industry and to the way polymers are used now. So this now is going to be our monomer, styrene. And so its individual, the monomer has a molecular weight of 104.15. We're going to then make polystyrene that has varying molecular weights, and we're not doing anything. You can do things with polystyrene to make it have a specific molecular weight. We're not doing anything in our synthesis to give it a specific molecular weight. So you'll get what you get, okay? But the polymers vary on what type of, how big is the molecular weight, what is the chemical composition, what is the shape, so the macromolecular architecture like I was talking about, and then how it is processed once it is synthesized, okay? So now what we're going to do is we'll talk about more specifically what we're looking at with our polymer and our reaction this week, okay? And so, like I said, we're only getting through step 1 this week. And with that, I'm going to put the reaction back up here again. There's a couple things we need to watch out for with putting this reaction together. So, our ethylbenzene is a liquid. We're going to react it with NBS. This is a solid. We're going to have our benzoyl peroxide present. So this is going to be our source of bromine. This is going to be our radical initiator, so I'll talk about each of those here. And again, the reaction is taking place in hexane, and it's refluxing for an hour, and then you'll get your bromoethylbenzene. Now, what position are we brominating with this reaction? Any thoughts on that one yet? Have you guys covered that? Anything off of an aromatic ring? What this position is? Have you guys talked about that?
The benzoyl position?
Yes, that is the benzoic position, okay? And it's really important that you understand why it is brominating there, okay? Because basically, with this guy versus hexane, they're very similar, right? So how can we use hexane as the solvent and only get bromination at the benzoic position? What does that tell you about that position on the molecule? It's very reactive at the benzoic position. And the reason for that, when you get into aromatic chemistry, you're going to talk about how the aromatic ring can stabilize that position. Okay, so this is a super reactive position, and you're not going to have any trouble with brominating your hexane solvent, okay, because it's just so much more reactive. So what you've got to do is when you get this product this week, you've also got to be very careful with it because it is very reactive. Once it's brominated, doesn't mean it's done reacting. It's very reactive at that position as well, okay? And so things that are halogenated like this that are reactive are very light sensitive and very air sensitive. So you'll have to be careful once you have your product to keep it out of the light and keep it away from too much air exposure. Now, one thing with peroxides is they are very reactive. That's why they are a good radical initiator. but they can be so reactive that they actually can be explosive, okay? So we have to be careful with our peroxides. Now, benzoyl peroxide is not, like, you weighing it out is not just going to spontaneously start reacting, but you just have to be careful of it, okay? So things you want to watch out for is not to get a lot of benzoyl peroxide stuck on the neck of the reaction flask when you add it to your reaction flask. Don't have it have any real contact between like spatula and other things, so you don't want to crush like your spatula with other things once you have benzoyl peroxide on it. You just want to be aware of this so that you don't do things to cause friction that would then make it want to react even more, okay? So we store our benzoyl peroxide in the freezer until right before we use it. Make sure you only use what you need. This bag, you need 0.25 grams, okay? So weigh out only what you need of it. You need just a very tiny amount for it to be the initiator, okay? Now the other thing with this reflux, you need heat to get started. So that's why we are refluxing it. But once you've added the heat, it's going to then take off on its own little reaction path, okay? And so once you've added the heat, it actually then starts its own exothermic reaction path, okay? So you're probably going to need to turn down the heat once it starts, okay? And you want to pay attention to it. This isn't a reflux that you want to just set up and walk away for an hour and come back and see what you've got, okay? You want to be watching it once you've got started refluxing. Turn down the heat once the exotherm starts, and you'll see it happen. It's not something that'll be questionable. But the thing is you don't want to stop the reflux when you do this. So you need to turn it down slightly, but don't stop it refluxing, okay? So on your omites, typically anything really below 50 really doesn't give it much heat, so you don't want to go below 50 when you're turning things down to take care of this exotherm, okay? So our NBS is important because we need that as our source of bromine. But we don't want to just put a bunch of bromine there for it to react and then, let the reaction take place, and then we'll have our product and everything will be set at the end. If we have too much bromine present, that's going to cause a problem with the reaction. So we instead use this N-bromosuccinimide as the source of the bromine. And so what that does is it provides a slow and steady source of bromine instead of having all the bromine you're going to use present all at once. And so what happens is the NBS will react with HBr, and I'll show you here in a little bit how this comes into play. And when it reacts with the HBr, you go from the N-bromosuccinimide to the succinimide. And then we get our source of bromine. So we need this reaction happening, and then as this reaction is happening, it'll be supplying bromine, but we won't be having it all supplied all at once. This is succinimide. Now, as this is happening, watch your reaction. You may actually see the generation of the bromine happening in your reaction. So from experiment 6, what color is bromine? orange-red. So you'll kind of see an orange-reddish tinge to parts of your reaction as the reaction is taking place and the bromine's being generated, and then it'll disappear as it's being consumed, okay? You may also see bromine speckles getting hung up in the condenser of the reflux. That's because the bromine's being generated, but then it's up in your condenser and it's not reacting, okay? So watch for the generation of the bromine. Now, a note about this succinimide is this is a nice off-white solid. It looks like, at the end of the reaction, it looks like what you should be keeping. Like when you finish your reaction, you're going to have this solution with this nice off-white solid floating around in it, so it looks like you should just filter your reaction and take the solid. Well, the problem is this is a byproduct. You don't want this, okay? So we want the liquid, we do not want the solid. So we're going to remove it with gravity filtration at the end of the reaction. And then this goes into the organic waste container, okay? So we'll filter it, we'll rinse it well with hexane to make sure we've got all our product, which is soluble in hexane, off of it. And then this goes into the organic waste container with acetone. So it does not go in the garbage or anywhere else. Make sure this goes in organic waste. And make sure you dissolve it with some acetone, okay? Now our benzoyl peroxide whenever it has light and or heat around, it decomposes into radicals. So this is a very reactive bond right here. And so it's very easy to generate this is our radical initiator, and it just takes a little bit of light and heat to generate that, okay? So this is what's forming at the start of the reflux that then adds the PEP to the reaction to then get the rest of the radical chain reaction going, okay? And so we get this is just an initial source of radicals to get things started, and then from there the rest of the reaction will occur. So since it is a radical reaction, we have our usual steps, which are radical chain reaction. What do you usually have? Initiation, propagation, and termination. So for our reaction, and this initiation is beyond our initial source of radicals to just get things started. We've got our BR2, so that comes from our MBS, and we have any heat or light. And we'll generate our bromine radicals, okay? Then our propagation is using those bromine radicals. So we've got our ethylbenzene. And it'll react with our bromine once it's generated. And we'll have then it, I'm going to use our radical first. We've got nothing to work with. So we've got, from our hydrogen, we've got one radical going this way. Another radical. So our bromine radical is going to react at our benzylic position, and we'll use, we'll react at that hydrogen. So this reaction is a free radical substitution because we're going to substitute our bromine at where we've already got this hydrogen, okay? So then, when we do that, then first we form, before we get the substitution, first we form our ethylbenzene radical, okay? And then we get our HBr, which our HBr is then going to be used with the NBS to keep generating bromine. So that's step one. Step two, then we have our ethylbenzene radical. And it'll react with bromine and so then we will get our product plus then more bromine radical to be thrown in to the whole mix, okay? And then our termination is just the combining of any two radicals. And so for this reaction, when we talked about the stabilization of the aromatic ring and stabilizing what's going on at this benzylic position, in this case, it's stabilizing this benzylic radical. That's what that aromatic ring is helping to stabilize. And so because the radical is stabilized at this position with the help of the aromatic ring, that's why we've got reaction occurring here versus occurring at any point along the hexane chain, okay? Now, once you get your product this week, okay, so you're going to, like I said, you're going to filter off your 6-cinnamon, then you're going to have your hexane and product all together. You're going to do a simple distillation to remove the hexane, just like you've done in the past. We do a good job of really pushing the hexane off of your product. Then you're going to have your bromoethylbenzene, okay? And you're starting with 5 mils of ethylbenzene, so in the end, you should get somewhere close to 5-ish mils of product, okay? What information we need about this guy is we are going to need its yield, so we need to know how much it weighs in grams. We also need its volume. So you need to take both of those measurements. And the reason you need the volume is next week, in part 2, you'll be doing a reaction that the styrene is generated through the process of a distillation. The first thing that's going to be come off is hexane. So we need to know the volume of your product here to then figure out how much of this was actually hexane, to then go back and recalculate yield once we have that information next week, okay? So no matter how hard you push your distillation this week, there is going to be a little bit of residual hexane left that you can't get off, okay? But you want to try and get as much off as possible. Then what you want to make sure you do is you store this in a tightly sealed vial, okay? With minimal airspace, okay? So you want the smallest vial that you can use, okay? And we're going to store it in the dark. Okay, and so what you'll want to do is, the reason we're taking these precautions is now this bromoethylbenzene is super reactive, okay, and it's super reactive with light and air. So take observations of what your product looks like before you store it, because most likely it will, even with these precautions, react a little bit and look different than what it does this week. Okay, so make sure you know what it looks like. Before you've got it completely stored away, after you've figured out your yield and your volume, okay, we need to do a couple tests. So the first test you're going to do is a water density test. So you'll have 2 test tubes, okay? One, and you're going to have like 0.5 to at most a milliliter of water in each of them, okay? The first test tube you're going to put a drop of ethyl benzene in it and see, is ethyl benzene more or less dense than water? Does it float on top of the water or does it sink to the bottom? Okay. The second test tube, you're going to use your product. You're going to put a drop of it in the test tube and see, does it float to or float on top or sink to the bottom. So with the ethyl benzene, what do you expect is going to happen with that? What do you think will happen? And what you know about other similar organic compounds? Is it more or less dense than water? It's less dense, so you should see it float versus sink, right? When you halogenate things, typically you make them more dense than water, okay? And so with the product, you want to be able to see it sink. Now, if you didn't take all the hexane off, you may get like a questionable test where part of it floats and part of it sinks, or it kind of halfway floats and sinks. So if you get a questionable test with this, what you can do is also do the Beilstein flame test to test that you now have bromine present. Because if you test a little bit of your product, and remember, put it in a separate test tube so you don't contaminate all of your product, you should still get the green flame like you did with experiment 6 if you had a halogen, okay? And then with this test, it's just really important, make sure you only use a 0.5 ml to a milliliter of water for the test. Do not use more than that, because what we need to be able to do is dispose of this in organic waste, okay? Our second test is the silver nitrate test. And so you'll have your bromoethyl benzene, and this is very similar to what you did in qualitative analysis in Gen Chem. Bromoethyl benzene, you reacted with silver nitrate, you get a displacement reaction, and so again, at that benzoic position, we'll get this cation that's formed, and then we'll get silver bromide that is formed that is a white to yellowish solid. And so if you'll follow the instructions in your lab manual for this test, and in the end what you should see is this solid form, which confirms that the silver nitrate had something to react with, which is the bromine from your bromoethyl benzene. Let this test sit 5-ish minutes or so. Sometimes it doesn't immediately form a ton of solid, okay? So set up the test and then walk away for 5 minutes and then check it when you're done. And then, like I said, when you're all done with this, you want to store everything sealed in a vial with minimal airspace, tightly sealed in the back of your lab drawer for next week, so it's in the dark as much as possible. Now, a couple things for your pre-lab as well as the report, okay? So your pre-lab is going to be a lot like your pre-lab for experiment 3, where we've got reactions, we've got a physical data table, we've got flow diagrams to show for each of our steps, and calculations to show. And so the report itself, when we get to that point, is worth 75 points instead of just 50, because we've got the 3 reactions that we're talking about, okay? And I'll give you something here in a little bit to help you prep that pre-lab. Couple notes for the pre-lab. So you have 3 reactions. You're going to have to show 3 yield calculations. So steps 1 and 2, you're going to, just like you have previously with experiment 3, you had to calculate a theoretical yield, and then you're going to calculate a percent yield. So you need to show a calculation in your pre-lab for step 1, theoretical yield and percent yield, for step 2, theoretical yield and percent yield. Okay, so there's 2 sets of these calculations, all right? And as far as step 2, assume you make 100% of your bromoethylbenzene in step 1 to be able to go on to step 2, okay? Step 3, we can't really do this when we set up the polymerization reaction. So step 3's yield calculation, you're going to use the grams of polystyrene that you end up forming. And so in your pre-lab, it's how much grams of polystyrene in theory should you form over the grams of styrene that you use for the reaction, and then times 100%, okay? So this is, for step 3, your yield calculation is really a weight percent calculation, or kind of like a recovery calculation like you've done previously. Ideally, for as many grams of styrene we put in, we get that many grams of polystyrene out. Okay? But probably that won't be the case. All right? Okay, so now let's look at, I'm going to put up this data table for you guys to look at, and then in a couple minutes here, we're going to have someone from a chem club come and talk to you guys too. So what I have here is data table for your pre-lab. So that's kind of like the bonus gift for coming to lab lecture today, is you've got your data table already started for your pre-lab. Okay. So I've got all of the reagents listed that you're going to need. You won't need dichloromethane. Okay. That was something we used previously. So I've got the physical data for each of these reagents and products, and then you need to fill out, you'll have to calculate the amount in moles for each of these columns, okay? You also will then need to calculate information for these chemicals, for these solvents. So for styrene, which I've already given you part of that, you'll need information for methanol, and you'll need information for THF, or tetrahydrofuran, okay? So here is the start of your pre-lab information. I'll save you having to look up all of that information, okay? And then, like I said, in a couple minutes we should have Chem Club coming in. Are there any questions you guys have while you're recording somehow? Old school, new school? No questions? Just make sure if you come down, you're not blocking someone else's view. Can we pause for the picture? Stop recording. You have that. Huh? You have that.